Hi class. Today we're going to go through numerical integration as a way to look at reaction kinetics. I have up here the simplest reaction we can think of, which is a unimolecular reaction of A goes to B at a rate constant of K1. As you know, we can readily write down the rate law for this as the velocity is equal to K1 times the concentration of A, and this is equal to the rate of minus dA dt, which is also equal to the rate of the formation d of B with time, dB dt. Normally, if we want to know how the concentration of A changes with t, what we would do is to integrate this equation. We would gather our A terms on the left side and our T terms on the right side, and we would integrate this equation from time equals 0 to T, which goes from A naught to A. Using a couple steps not shown here, we know that we would get the natural log of A on the left, and we get minus KT on the right. We would substitute in the limits and evaluate the integrals, and that would lead us to this expression right here, which is the famous familiar one, that A is equal to A naught, and this decays as E to the minus KT. You can see here a nice plot of this in which the concentration of A is decreasing with time and starting at a value of A naught. While this particular reaction mechanism is exceptionally simple, A goes to B, and fairly easy to solve, it turns out that in many cases reaction mechanisms get much more complex, as you're familiar with. One is shown here on the next slide, and this is our familiar reaction mechanism in which we have enzyme binding to substrate to give the Michaelis complex, which then reacts with a rate constant K2 or Kcat to give back enzyme plus product. In this particular instance, it's much harder to integrate the rate laws, but it's not difficult to write those rate laws down. We've done that before, and it's shown here with the example of the change of the concentration of ES with time, and we know that we form ES by combining E plus S at a rate constant K1. That's the first term here in the rate law. We also know that ES can break down by two different channels. It can decay at a rate constant of K minus 1 or a rate constant of K2. And those two terms are shown here. Here's the decay through the K minus 1 channel, and here's the term for the decay through the K2 channel. But fortunately, we don't have to solve the rate law and integrate it in order to get a good estimate of what happens with the concentration of ES with time, or ES shown here, or even with E, S, or P. In other words, all four of the species, E, S, ES, and P, we can estimate how those change with time through a process called numerical integration. And I'm going to show you that using an Excel spreadsheet that Erica prepared for us. So here's a simple Excel spreadsheet in which we're looking again at the first simple reaction of A goes to B, right here, and we can write down the rate law for this, that dA dt is equal to minus K times A. But we can carry the dt term over onto the right-hand side of the equation to see how A changes with small changes in time. And if we know how A changes, then we can predict accurately the concentration of A at some delta t time later. And that's shown here in this simulation. So we start with an arbitrary initial concentration of A, here 1 millimolar at time 0, and then we look at how the concentration of A is going to change with time. And so dA is calculated by multiplying together minus K times the concentration of A times our delta T. So if I go over here to where that is, and I actually click on this particular cell, or if I double click, you can see here now, let me try that again. If I double click on this, okay, that's better, we can see that dA is in fact comes from these three terms. So the minus K is this cell B5, and notice the two dollar signs, which means we're going to hold that constant. The next term is from C5, that's the concentration of A, so that's our second term here. And then the third term comes from constant cell A8, which is shown over here, and that is our delta T. So in other words, our dA is coming from the multiplication of these three terms, K, A, and dt. K, A, and dt. Now, once we know dA, we can calculate A at some small time later as equal to the initial concentration of A plus the change. So if I look here and I click on that, we can see that this cell, which is equal to cell C6, comes from the sum of A and the change of A. And we can go down to, say, the next cell, and we can do a similar calculation. So if I escape here, we can see that this guy is also calculated in those sorts of terms. So now we've generated a column of A and time, and we can plot those, and that's what's shown here. We've plotted A versus T, and we've done it for two different rate constants, and so there's one set of data that is shown here and a second set that's shown here. The first set has a smaller k set at 0.01. The second has a larger k, 5 times larger, set at 0.05. And so if I go over and click on one of these set of data, we can see here that this set correlates with the smaller rate constant 0.01, and this set goes with the faster set of data at 0.05. And you can kind of see that the half-life is about 5 times longer for this. Now, the beauty of this, there's actually two advantages. One is that we didn't have to solve the rate law, we didn't have to integrate, we just simply had to write down the rate law. And the second is that I can quickly change these values and see what happens. So for example, let's go over and make this decay 2 times faster. So I simply can go in and change this number from 0.01 to 0.02, and what you'll see is the blue curve should decay twice as fast. And there it goes. We can see that it's now going down twice as fast. So while this is a very simple case, it illustrates the principles. So now what I want to do is take you to a second simulation that Erica set up for us. And this involves the enzyme reaction. And if I make this screen a little bit bigger, we can now follow what happens here as well. And so here is the mechanism that we're interested in. It's the same one that I drew out for you a few minutes ago on the chalkboard, and it involves the one that we're familiar with, enzyme and substrate binding together to give us the Michaelis constant complex ES, and this decaying to give enzyme plus product. And we can write down the rate laws by inspection very easily. So Erica's written down here the first rate law, which is for dE dt, and we can see that we lose E with time due to the formation of E and S, and that's shown here, E and S, at the forward rate constant K1, and there's a minus sign for loss. But we also form E by two different channels. ES can go backwards to give E plus S, or it can go forward to give E plus P. So we have ES times K minus 1 for that one, or we have ES times K2 for this particular process. And so over here again, we have time, we have a dt, and we have that as our increment. We have an initial concentration of E, In this case, Erica chose an initial concentration of 10 micromolar, and then we have dE. And dE is calculated from this equation here, in which dt is carried over and multiplied by these three particular terms. So if I go in and now click on this particular cell, G6, we can see here our dt is right here at B8, and then we can see the three terms which correspond to these three terms that are going to be multiplied by dt. The first term has three terms within it, which are going to be K1, E, and then S, which is hidden underneath here, and so on and so forth. So we can see here that our second term, which is going to be K2, which comes from the constant cell D5, I'm sorry, in this case K-1, which comes from the constant cell D5, multiplied by J5, which is ES. And then the third term has the constant cell C5, which is K2, again times ES, the whole quantity times dt. So you can see it's quite simple to write this in. This gives us the change in E. And then at some time later, right here, we can go in and we can calculate the new E as the old E plus dE. And Erica went through and did similar calculations for S, and it has its ds column, which is calculated from the rate law, and I can show that to you by clicking here. Let me escape out of that. Double clicking here, and we can see where it's calculated from. I won't take the time to go through that in detail, but I think you all know how to write the rate law down for ds and to calculate the change in S, and then to add that to S. And we have similar terms here for the change in ES with time, or the change in ES, which is multiplied by dt, and then the change in product. And then Erica made a nice plot of each of these four species with time. And so, for example, if I click on this curve, which is S, you can see that over here the S and the T columns are highlighted, and as expected, what happens is that S, which is set at 100 micromolar, or 10 times the enzyme concentration, so this is a multiple turnover experiment that can have 10 turnovers. You see what happens is that S gets used up with time and decays down to 0. Likewise, that SP increases with time and starts from 0 and increases to a final concentration that's equal to the initial concentration of S as expected. If we look at ES, which is in the cyan color, we can see that the steady state assumption pretty much holds in the sense that ES doesn't change with time. That is, dES dt is pretty much equal to 0. Eventually it decays away. And the enzyme starts out at this initial value of 10 micromolar, as we expected, and it goes almost down to 0 because the enzyme is all tied up as ES. So E plus ES, their sum has to go to 10 micromolar. But eventually, as ES is used up, the E returns back to its original value of 10 micromolar. So let me just summarize by saying a couple things about this more complex case. First, it's very difficult to solve the rate laws and integrate them for this particular example, and progressively harder for progressively more complex cases. However, it's trivial to write down the rate laws, and therefore trivial to calculate the concentration of, say, E at some time delta t later. And that allows us to quickly plot the data and give us a chance to basically get a feel for how the reactions change with time and depend on concentration and depend on rate constants. So we can go in and we can change these rate constants and see what happens. So Erica set her K1 at 0.1 inverse second, or what is equivalent to 10 to the 5th per molar per second. But let's go ahead and change that number. And when we do, these curves to the right will change. So let's try making it, instead of 0.1, let's try making it let's say 0.5. And we can see that the curves changed. And then I can do the undo key and make it go back. And I can see, well, how do the curves depend on the value of K2? Right now it's set at 2. Let's set it to 1. And again, the curves change. And I can undo. And I can redo. Undo, redo. And let's go ahead and, last but not least, play with the value of K minus 1. This is the return rate constant from ES. Right now it's set at 0.01. Let's set it to 0.05. And when I do that, oh look, there was very little change. Okay, can hardly see it at all. Undo, whoops, redo, redo, undo. So this is a fact. Well, let's try something. Instead of changing it just to 0.05, let's try changing it to 0.5. Again, relatively little effect. So this is how we can begin to develop insight. So now I'm going to switch to one more program, and this is going to be the Kinetics simulation, which does numerical integration and does this in a much fancier way. But hopefully these first two segments of this particular lesson give you a feel for where numerical integration comes from and how it works. So now up on my screen I have the Kinetics Explorer program. You can see here, I think, that this is the Kinetics Explorer Student Edition. And this program was developed by Ken Johnson, formerly at Penn State, and someone who I collaborated with on my PhD work. One of the leading kineticists in the world. And this particular program is free. You can go ahead, if you Google it, Kinetics Explorer, you can download the student version and use it free of charge. The only thing it does not allow you to do is to import your data and to fit your data. In order to do that, you have to purchase the key. But I recommend that everyone go and get the free version and go ahead and try it out and see how you like it and see the insight it gives you. And if you do need to fit your data and globally fit it, then consider going ahead and buying the full version of this. So I'm just going to take a few minutes and walk you through some of the features. And this particular example was put together by Jamie, and let me see if I can show you some of the different features. So one of the first things that you'll notice over here is that you can edit and input the model that you're interested in. And I'm going to go ahead first and just make the screen a little bit bigger. And so the model that we have here is, again, our familiar model, enzyme plus substrate, bind to give the Michaelis complex ES, which then decays to give us enzyme plus product. The equal signs mean that there's an equilibrium in the first step and in the second step. I'll show you in just a second that we can make steps irreversible by leaving in the equal sign for the equilibrium, but by setting the reverse rate constant equal to 0. And so it's relatively easy if we're interested to go in and to edit the model. And so we can just go in here and we can change it around. We can put additional steps in. If I wanted to, I could delete or add back various species. But for now, I'm just going to go ahead and use the reaction that Jamie already put in here. I'm just going to cancel out of this. And we're going to do a continuous simulation, and we're going to visualize the model, which means that we can see the model over here. And in fact, I can move it around like this. And notice that the substrate is shown above the arrow, and this is to imply a pseudo first order reaction mechanism where S is in huge excess, just like we've talked about in some of the previous lectures that we did over the summer. And likewise, where P is released, we can also think of P binding as we go in the reverse direction in a pseudo first order fashion, and hence that's why it's drawn in this fashion. And you can go in and you can play around with these and change the directions and so on. And I think that's useful for more complex examples. So in our little tour here of the Kinetics Explorer student version, there's a variety of things we can do, but one of the first things I'm going to do is I'm going to go over here on this left column, and I'm going to scroll, and I'm going to go down, and I'm going to find a portion here which tells us the concentrations, the initial concentrations of E and S, and ES and P. And you can see that we can put multiple values in, but for now, I just want to put a single value in. I'm going to remove the 20 and just leave the 10. And now you can see that there's a single trace for each of the colors which correspond to the various species. So red here is E, and green is ES, and blue is substrate decaying, and yellow is product building in. And this looks pretty similar to what I showed you from what Erica built with her Excel simulation. In fact, if I now scroll back up, I can look at the rate constants, and I can see here that the rate constant that's in the simulation right now for K1 is 0.05. And I also should mention that these rate constants are unitless. And that makes sense when you realize that the units don't matter as long as the units are constant. In this particular example, we're going to assume that this rate constant is inverse micromolar inverse second. And if I tab back to the Excel simulation that Erica made, you can see over here I used a K1 of 0.1. And so let's go over here to our K1 and let's change that to 0.01. And one of the cool things that we can do is we can go in and we can, well, first off we can go in and we can change that. We see the curves changed. Okay, but if we want to change it, instead of just typing in the number one at a time, oh, I'm sorry, I want this to be 0.1. Okay. Right, so again, I would like this number to be 0.1 so that it agrees with the value from the Excel simulation. And then K2 should be 1, K minus 1 should be 0.5. So K minus 1 here should be 0.5. And the value for K2 again should be 1. I'll go ahead and change that to 1. So again, as we change those numbers, you could see over here on the right side that our particular traces were changing in fairly profound ways. But one of the cool features about the Kinetics Explorer is that we can just grab a hold of one of these rate constants and we can slide it up and down. So go ahead and grab hold of K1 and I can move it up and down. And if I had real data here, I could swing it until those curves overlay with my data and get a good guess as to what's going on. And I'm going to go ahead and grab a hold of K2 and see what happens. You can see it does something different. And then lastly, I'm going to go ahead and grab a hold of K minus 1, and we can see that that has an effect up to a point. So it has an effect, and now I'm pulling it down, and it looks like when I hit about 0.2, as I pull it down more and more and more and more, it doesn't matter. And so there's ranges where the rate constants affect the traces, and then there's ranges where they do not, and it's quite interesting. So again, let me put it back to Erica's value, which was 0.5. I can go ahead and I can type that in. As I had up earlier, I can also look at a series of different substrate concentrations and see how those traces look. And let's say I had 4 sets of data, then I could see how, and each one was at a different substrate concentration. I could put in those different substrate concentrations and see how the traces overlay my data. So the way to do that is I simply go down here to where the data is entered and go ahead and click with my mouse in that particular area, and I can add, let's say I want to see what 20 looks like, and 50, and 100 micromolar substrate. So now I should get 4 yellow traces, and I do, and we can see them here. You can also see, though, that we can see that the particular yellow traces with product are, some of these are not getting complete. So I can go over here where time is, and I can grab a hold of the time, and I can move that up and down to look at longer times. And it's kind of interesting, right? So not only are these color coded, but they're shaded. So the light, very light shade guys go together, and so we can see that the loss in substrate and the gain in product go together. So this particular curve corresponds to my initial concentration of 100 micromolar. It starts at 100. We can see how it goes down, and then we can see that the product for this also builds into 100. And my next concentration starts at 50, and it's there, and we can see that this is the sort of the medium shade, and this one goes up to 50, and so on and so forth. The 20 with the 20, and the 10 with the 10. So you can see again the various traces here. I'm going to go back over here and simplify things down and go back to just a single substrate concentration again. So let's just go back and put it back at 10. And again, we can see just a single trace, one product in yellow formed with time, and one substrate used up in blue with time. But I also might be interested in plotting something other than concentrations. I might be interested, for example, in ribozyme reactions, we often look at the fraction of substrate with time. So I can go over here into this other window, and I'll choose S5, and I might be interested in how much P forms with time. And this is fraction P, so it's P divided by the sum of all forms of the substrate. And that substrate can be present as S, it can be in the Michaelis complex as ES, or it could also be present as P. And so I'll go ahead and do that. And now we can see in cyan here the fraction of product, and we can see it goes from 0 to 1, and it increases with time, and it reaches a maximum right about at the same time that the product reaches a maximum. It's a little hard to see this, so it turns out it has another feature that you can zoom in. If you just use your mouse and highlight over the part of the data that you're interested in, let go, it will highlight that point. So now we can see nicely the fraction product increasing from 0 to 1 with time. And I want to show you just one last cool feature, and that is that you can easily plot and prepare and plot free energy diagrams. So back up here where the rate constants are, you can just go over and click on the free energy term, and when you do that, you can see this very nice free energy diagram that's generated. So go ahead and close that. So that's the end of today's lecture. Just a super brief overview. I started out by showing you some simple reactions. A goes to B, the simplest one we can think of, and then the simplest enzyme reaction that we have, enzyme and substrate going to make a Michaelis constant going to E plus P. We reviewed how to integrate a rate equation for A goes to B, and to then plot the concentration of A and seeing it decaying with time. We also looked at the rate law for the Michaelis complex example, but we saw that that would be much more difficult to integrate. We then went in and used numerical integration in an Excel example. We used it both for the simple A goes to B, and we saw that we could recapitulate the same types of decays, and we could also change the rate constants and see what happens in real time. We then did that for the Michaelis example. It was almost just as easy to write down the rate laws, but would have been much harder to integrate it. Yet we could use numerical integration to see what happens with each of the species, E, S, ES, and P with time. And then we looked at a commercial program that also does numerical integration called Kinetics Explorer, and we saw it do similar sorts of things, but that it was much more powerful and that we could grab a hold of the rate constants and change them, move them up and down, and see in real time what happens. And then we could also look at multiple substrate concentrations. We also saw that there were different ways that we could output the data, that we could look not only at concentrations but at fraction. You could also use this to look at to set it up to look at, say, a spectroscopic output such as fluorescence as a function of time. And we also saw that it could allow us to prepare free energy diagrams. So hopefully this is a new tool that will empower you in your investigations into enzyme kinetics. See you next time.